All right, so in class today we looked at what a limit was and did a little bit of exploring with limits. So what we're going to look at today is the more finite definition. And what this is going to help us do is it's going to help us graph things with asymptotes. That's kind of one of the things with limits that we do. It's also a major topic in calculus. So it's something you're going to learn also later in your math careers. So we're going to start with pretty basic things today with limits, and that is mostly just how to find it by looking at an equation or a graph, because there's a couple different ways you can go about finding a limit. So this first one, we have a line, f of x equals 2x plus 3, and we're going to find the limit as x approaches 1. So this right here tells us the x value that we're trying to match a y value with. So the first thing I'm going to do is sketch the graph of this line. So we have y-intercept of 3, and our slope is up 2 over 1, or we can go down 2 over negative 1, and then up 2 over 1. So we have our line. So this number, the 1, tells us the x value that we're going to look at. So this is our x value that we're trying to see what the limit is. The limit stands for the y value you get when you approach the x value. So my y values, as I approach from the left, are getting closer and closer to 5. So as it's approaching from this side, the y value is approaching 5. When I come from this direction, from the positive direction, my y value is also approaching 5. If these are approaching the same number, then that means your limit is 5, whatever that number might be. So one of the key things with limits is your limit is a y value as you come to an x value. So if we look at number 2, we have another graph. Down here, we're going to look to see what is our y value as we approach 2 for x. So here's my x equals 2. So if I come from the positive, my y value here is going to be approaching 0. This direction, the negative direction, the y value is negative 2. Since these don't match, we have no limit, or we write does not exist. And this is usually where people quote Mean Girls, because the limit doesn't exist here. And we'll talk about the types of limits that don't exist a little bit more as the unit goes on. But for right now, if these two y values from the right and the left don't match, or from the positive and negative don't match, you have no limit. Okay, on number 3, so here we have the limit as x approaches negative 5, so that's the x value, and we have an equation. So yes, we could graph, but the type of equation that we take a limit of sometimes gives us other methods for finding a limit. This is a polynomial. Polynomials are known as well-behaved functions. And what it means to be well-behaved is we don't have any fractions or anything that could potentially give us an undefined. Polynomial functions are nice graphs or nice functions to graph. So we're not going to have any of this disjointed stuff or open circles, closed circles bouncing around on our graph, because it's a well-behaved. So if you have a well-behaved function, you can do something called direct substitution. So direct substitution means we substitute in our x value into our equation and simplify, just like if we were going to evaluate it. So we would get negative 5 squared minus 4. We would get 21 as our limit. Okay, again, direct substitution only works if you have a well-behaved function. And polynomial functions do the same thing. So if we go back to number 1, this line, 2x plus 3, that's a polynomial. So if we wanted to, we could have done 2 times 1 plus 3, and we still would have gotten our limit of 5. Okay, if we don't have a well-behaved function, so if we look at number 4, 4 is an example of a not well-behaved because it has a fraction with x in the denominator, which means I'm going to have an open circle somewhere. That right there tells me it's not well-behaved. So I can't do direct substitution. So in order to do something like number 4, we're going to have to graph it. And we'll learn a couple of other methods we could do in a day or two that can help us do it without graphing. But for right now, you just sketch the graph. And feel free on your sketches to use Desmos or a graphing calculator if that's what you need to get a sketch accurate enough to find the limit. So here we're finding the limit as x approaches 1. So from the negative side, I'm approaching my y value. Since it's an asymptote, my y value is just going to keep going lower and lower and lower, meaning it's approaching negative infinity. From the right side, my y value is going up and up and up, approaching infinity. If these do not match, then we say it does not exist. And you can just abbreviate that DNE. Okay, and then the last one I want to do right now with you guys is number 5. And I have 2 more, one that's kind of like a test question that we're going to do in class. But for right now, we have the limit as x approaches 7. So let's look at our equation and ask ourselves, is that a polynomial? Because if it's a polynomial, then we can do direct substitution. This one is a polynomial. It doesn't have any fractions or anything weird. So that means I can do direct substitution. So 7 squared minus 4 times 7. So we'll get 49 minus 28. And we'll get 21. So what this means is, with what we just found, is that if we were to graph it and do our limit like we did on 2 and 4, that the y value would be about 21. Now we're going to do 2 more in class that are not well behaved, because those are the ones that sometimes have some alternate methods, and we're going to go over those in class. But this is the basic idea to a limit. Either you can graph it and you're looking for the y value that it approaches as it approaches a certain x. If it's a polynomial and it's well behaved, then you can do direct substitution to find that number rather than graphing. We're going to explore a couple of other methods for finding limits that don't require us to graph. But for right now, if you need to graph it, graph it. If it's a polynomial, do direct substitution.